So can beets really beat rust? I know, it sounds a little out there, but what if we could solve one of engineering's oldest and most expensive problems with a common vegetable? It sounds unlikely, but some fascinating new research is asking that exact question.
Seriously, just think about it for a second. Stopping rust using vegetables? It sounds like something straight out of a sci-fi movie. But we're about to see how scientists are using some serious supercomputing power to turn the humble beetroot into a high-tech weapon against corrosion.
But before we get to the beets, we really need to understand why this is such a huge deal. We have to wrap our heads around the sheer scale of the problem. Because rust, well, it's so much more than just an ugly patch on your car. It's a massive, hidden crisis happening all around us.
Now, when I say massive, I mean it. Get a load of this number, 3.4% of the entire world's GDP. Let that sink in for a moment. That's the estimated annual cost of corrosion. We're talking trillions of dollars just gone, wiped out every single year by the slow, silent decay of metal.
You know, that mind-boggling cost isn't just about replacing a few rusty parts. Not at all. It's about the safety and the longevity of our entire world. Our bridges, our pipelines, our buildings. When the steel rebar inside a concrete pillar starts to corrode, the whole structure is suddenly at risk.
For decades, we fought back with chemical inhibitors. The problem is, the conventional ones, while they work, often have a pretty dark side. They can be toxic, really bad for the environment, and they're facing more and more restrictions. This has kicked off a huge push for so-called green inhibitors, which come from natural, renewable sources. The big challenge has always been, can we make the green stuff just as effective as the synthetic stuff?
So, if the old solutions are toxic, where do we find a better one? Well, the answer comes from a very, very unexpected place.
Yup, the humble beetroot. The secret is in molecules called betanes, which are derived from the very pigment that gives beets their deep red color. And what's really cool is this is a perfect example of the circular economy in action. You're taking what might be agricultural waste and turning it into a high-value, sustainable product.
And this isn't just a theory, not by a long shot. Previous studies have already shown that beetroot extracts can be incredibly effective, achieving, and I'm quoting here, inhibition efficiencies exceeding 90%. So that was the scientific foundation that inspired researchers to ask, okay, this is great, but can we make it even better?
So how do you take a good molecule from a beet and turn it into a great one? Well, the answer isn't in a chemistry lab with beakers and test tubes. It's in the world of high-performance computing.
That's right. Instead of spending years mixing chemicals in the lab, the scientists in this study used a powerful computational approach. This lets them design, model, and test brand new molecules completely virtually, which, as you can imagine, saves an immense amount of time and resources.
Their method really breaks down into two core steps. First, they use a technique called DFT to really understand how a molecule behaves. Then, they feed all that data into a predictive model called QSAR to figure out how to design even better ones.
Let's start with DFT, or density functional theory. Just think of it like creating a perfect digital twin of a steel surface and an inhibitor molecule. The computer then runs all the physics between them to calculate exactly how strongly that molecule will grab onto the metal. That stickiness is what creates the protective layer against rust. Okay, then comes QSAR. This is basically a machine learning model. It analyzes all the data from thousands of those DFT simulations and starts to learn the patterns. It figures out which properties like shape or size create the strongest bond. Then it can predict the performance of brand new molecules before they even exist. It's pretty amazing.
So we have the problem, the plant, and the process. The big question is, did it all work? Let's get to the results.
This table is where it all comes together. It shows something called adsorption energy, which is just a scientific way to measure sticking power. All you have to know is, the more negative the number, the stronger the bond. Now look at that B4 derivative. That's the molecule they designed from beetroot. It's at minus 172.1. When you compare that to a common synthetic inhibitor and another natural one, yeah, the beet molecule is the clear winner.
And this bar chart makes the results even clearer. You can just see it. The computationally designed beetroot derivative forms a significantly stronger protective bond on steel than the conventional synthetic inhibitor it was tested against. No contest.
To put a single number on it, the best beet-derived molecule showed a 7.5% stronger bond to the steel surface. Now that might not sound like a huge number, but in the world of materials science, that is a very meaningful improvement.
So here's the crucial point, the main takeaway from all this. This research challenges that old idea that sustainable alternatives are always a compromise. In this case, the green, biodegradable, beet-derived molecule, the one designed with cutting-edge science, actually outperformed the traditional, less environmentally friendly option.
So a beet-based molecule can outperform a synthetic one. That's fantastic. But what does a breakthrough like this actually mean for the bigger picture?
Well, the implications are huge. First, this approach turns agricultural byproducts into a valuable resource. Second, it gives industries a safer, biodegradable alternative to harsh chemicals. And all of that leads to longer-lasting, more sustainable infrastructure for all of us. But maybe most importantly, this computational method provides a powerful blueprint for discovering and designing a whole new generation of eco-friendly materials.
It really makes you wonder, doesn't it? If a solution this elegant and this powerful was just hiding inside a beetroot, what other profound secrets are locked away in the natural world, just waiting for the right scientific tools to come along and uncover them?